Good evening, everyone. Okay, last time we've practiced simplex algorithm with several different example problems, right? And today we were going to work on another in-class exercise problems. And at this time, from different point of view, we're going to solve the exercise problem. So, given a simplex table, we were going to investigate whether the current basic solution is optimal or non-optimal, or infeasible or feasible, unbounded, things like that, okay? And then we're going to continue to talk about the simplex algorithm, but at this time, we're going to deal with some special case in which the slack variable cannot be used. Okay. Okay, first of all, I want you to recall your memory. So last time, we've considered this example problem, right? And because there is no positive relative profit, in that case, we may say that this is the optimal table, right? However, there is a zero relative profit for a non-basic variable, which is S2. So in this case, we may conclude that the current LP have alternate optimum. Because non-basic variable S2 has a zero value of relative profit, which means increasing the value of S2 from 0 will not affect on the objective function value, right? And because the current objective function is maximize 0 times x1 this is the current objective function, right? Based on current simplex table, 0 times x1, 0 times x2, and minus 0.5 s1 plus 0 times s2, right? Which means increasing the value of s2 from 0 doesn't affect on the objective function value, right? Because 0 coefficient for that variable. So if we decide to include S2 variable as a basic variable, then we may have some same objective function value with different combination of basic variables, right? And this shows the graphical representation of this case, right? So every point on this edge, including 2 corner points, is optimal. However, only the 2 corner points are the basic solution. Is that right? And regarding this simplex table, because S1 variable has a positive relative profit, we may say that this is not the optimal table yet, right? And S1 column is selected as a pivot column, right? However, only the ratios of right-hand sides to positive substitution rates are used in the minimum ratio test. So in this case, we cannot perform the minimum ratio test, right? Because minimum ratio test provides no blocks on the increment of S1 variable. So in that case, we may conclude that the current LP is unbounded above, because this is the maximization problem, right? Okay, then now let's work on the in-class exercise problem. So in this in-class exercise problem, we will consider several simplex tables, right? And we assume that the objective in each case is to be maximized. And you are required to classify each table by writing a letter A through F according to the following descriptions. So the case A is the optimal table with alternate optimum, and case B is the optimal objective unbounded. Case C is non-optimal and non-degenerate table with bounded solution. And case D is the non-optimal but degenerate table with bounded. I just let you know that the LP is degenerate if at least one basic variable has a value of 0. Okay? And when this occurs, the next basis change may not result in an improvement in the objective function value. Okay? And case E is the unique optimum. And the last three, case F is the table with infeasible basic solution. Okay, then you remember we've learned that any LP must be either unique optimum or multiple optimum or infeasible or unbounded, right? So what can you say about this table? Just remind you, we are dealing with maximization problem, right? So is this optimal table? Yes, this is the optimal table. Why? Because there is no positive relative profit, right? Which means there is no positive coefficient in the objective function row. So this is the optimal table, right? But you should be careful. If you look at the right-hand side, one of them has a negative value, right? Here. What does it mean? One of the basic variable has a negative value. So this is the infeasible case, right? So the answer is F, table with infeasible basic solution. Is that right? Let me use the highlighter just in case. Okay, what about the next case? Is this optimal table? Again, we are dealing with maximization problem. No. We have lots of positive relative profit on this table, right? So this is not an optimal table. Then which variable you want to select to enter the basis? X1, just X1? We have a bunch of choices, right? X1 or X3 or X4 or X7 or X8, right? So we may choose any of them arbitrarily to enter the basis. So once you select entering variable, what is the next step in the simplex algorithm?
Choose the variable that leaves the basis.
Right. Select the leaving variable by performing the minimum ratio test. Is that right? But here, if you look at the right-hand side again, one of them is 0, right? Yeah. What does it mean? One of the basic variable, in this case, x5 variable, right? One of the basic variable, in this case x5, has a value of 0, which is called degenerate solution, right? I said for any LP, at least one basic variable has a value of 0, then we call this degenerate solution, okay? And I said if there is a degenerate solution, then the next iteration the objective function might not be improved. Okay? It could be, but so in this case, the answer is D, right? Non-optimal and degenerate table with bounded solution, right? Okay, then let's consider the third case. Is this optimal table? Yes? No? Yes? Yes. Because there is no positive relative profit, right? So this is an optimal table. And then is this infeasible? If you look at the right-hand side values, then there is no negative values, of course, except objective function rho, right? So definitely, this is not the infeasible case. And because we know that this is an optimal table, next you need to decide if it is a unique optimal or a multiple optimal, okay? Then how do you know if it is a multiple optimal? You remember? If the relative profit of any non-basic variable, okay, of any non-basic variable is 0, then we may say that we have alternate optimum, okay? So just like this, x7 variable, right? Currently, x7 is the non-basic variable, right? But it has 0 relative profit. So this is the case, okay? So in that case, increasing x7 variable from the value of 0 will not affect on the current objective function value, right? So in that case, we will have same objective function value with different combination of basic variables. So the answer is A, right? Optimal table with alternate optimum or multiple optimum or infinite number of optimal solutions, right? Any questions so far? Okay, then let's consider number 4. How about this table? Is it optimal table? No, because there is a positive relative profit. So this is not an optimal table. Then which variable you want to select to enter the basis? Yeah, we have only one choice, right? x4. So x4 column is selected as a pivot column, right? So again, once you have an entering variable, you can select leaving variable by performing the minimum ratio test, right? However, only ratios of right-hand sides to positive substitution rates can be used in minimum ratio test, right? So we cannot perform the minimum ratio test in this case, right? Because the minimum ratio test provides no blocks on the increase of x4 variable. So the current LP is unbounded. Is that right? So the answer is B, objective, unbounded, above, because we are dealing with maximization problem, right? Of course, for the minimization problem, it should be unbounded below, right? Okay, this is the final case, number 5. Is this optimal table? Yes, right? Because there is no positive relative profit. So this is an optimal table. And then is this infeasible? No. And because we know that this is the optimal table, again, you need to decide whether it's a unique optimum or the multiple optimum. Okay? Again, how do you know if it's a multiple optimum?
If a positive bracket is 0.
I'm sorry?
If the positive bracket is 0 for one of the basic values.
One of the non-basic variable, right? So let me say again, if the relative profit of any non-basic variable is 0, then we may say that we have an alternate optimum. Okay? So in this table, is there any non-basic variables whose relative profit is 0? So which variables are the non-basic variable at this time? x1, x3, x4, and x7, and x8, right? Those 5 variables are the non-basic variable. And all of them has either, or in that case, all of them has negative relative profit, right? So this is not the case for multiple optimum, right? This is the unique optimum, right? Because every non-basic variable in this table has a negative relative profit, which means the current table provides the unique optimum solution, right? So the answer is E, unique optimum. Okay? Does that make sense? Any questions so far regarding this in-class exercise problem? Okay. So we've known that the simplex method assumes that you have an initial table with a basic feasible solution. And so far, in LP problems solved by in LP problems solved by the simplex method, as the initial basic variables, we have used the objective, which is negative g, and the slack variables, right? Then how could you use the simplex method if the LP has no slack variable, which we can use for this purpose? Then let's consider an inequality constraint. It says 4x1 plus x2 is greater than equals 20, right? If the variable s were used as a basic variable for this equation, we would obtain an infeasible solution, which is s equals negative 20, right? So in this case, we need to add an artificial variable a, like this. And if we let this artificial variable a be the basic in this equation, then we obtain a pseudo-feasible solution with a equals 20. Okay? Okay, then let's consider another example. Suppose we are given with this LP model. Okay? First, modify the third constraint so that we have right-hand side is greater than or equals 0. Right? So we have negative x2 plus x4 equals 1. Next, add slack variable and subtract surplus variable to convert inequalities to equations. Now we can use negative g and s2 as the basic variables in the objective row and the second constraint. And the other constraints need artificial variable. Okay? Now, we can use negative g, a1, s2, and a3 and a4 as the basic variables in the respective equations, and getting a pseudo-feasible solution with basic variables, which is g equals 0, and a1 equals 4, s2 equals 6, a3 equals 1, and a4 equals 0. And of course the non-basic variables equal to 0, right? So we've learned that it's possible to obtain a pseudo-feasible basic solution using only a single artificial variable, right? So in this method, before adding the artificial variable, pivot an arbitrary variable into the basis in each constraint row. That is, slack or surplus variable for that row, if there is one. Okay? And in general, the result is a basic infeasible solution with one or more basic variables negative, right? Is that clear? Then let's take an example for this. In this example, as you can see here, second and the third constraints are greater than inequalities, right? So inequalities are converted to equations by the introduction of slack variables and surplus variables like this, right? And the initial table for the simplex algorithm would be constructed based on this standard LP, right? Now, choose an initial basis which are not necessarily feasible at this time, and then pivot variables into the basis. Then the resulting table becomes infeasible, like you see here, because two basic variables are negative, right? Here, S2 equals negative 4 and S3 equals negative 2, right? So this table provides infeasible solution. Now, for every row having an infeasible basic variable, let's insert negative A, like this. Of course, A is an artificial variable, okay? And then, if we pivot the artificial variable into the basis in the row with maximum infeasibility, that is most negative right-hand side, then the resulting table gives a pseudo-feasible basic solution. Okay? And the choice of initial basic variables, except for negative g, is arbitrary, actually. So, for example, if we arbitrarily select negative g, x1, x2, and x3 for basic variables in these three constraint rows and pivot them into the basis, the resulting table would be like this, right? And then subtract artificial variable in rows number 2 and number 3. then we will come up with this table. Okay? And then pivot in constraint row with most infeasibility. With the right-hand side of constraints, now non-negative. Is that right? Does that complicate a little bit? Okay, then let's consider another example. Okay? Just notice that all the constraints are equation at this time, right? So the initial table for the simplex algorithm would be constructed based on this standard LP, right? And we arbitrarily select variables x1, x2, and x3 for basic variables in the three constraints rows. In the three constraints rows. And pivot them into the basis. Then the resulting table would be like this, right? And subtract the artificial variable from rows number 2 and number 3, which have infeasibilities, right? Which has negative values on the right-hand side. Then we will come up with this table, right? And then pivot in the constraint row with maximum infeasibility. The resulting table is pseudo-feasible with non-negative right-hand side values, right? However, now the problem is this cannot be the optimal solution for the original problem. Why? Could you speak up, please?
There is a positive number and number x.
Opposite number, others. Or because this cannot be the optimal solution, because each artificial variable has some positive value. Actually, artificial variable should not be included in the optimal solution. Okay? Which means each artificial variables must be eliminated from the basis. And actually, the next two methods will make this possible. Okay? They are big M method and two-phase method. So first, let's talk about big M method. Okay? In big M method, we need to follow several steps like this. First, we need to modify the constraints so that the right-hand side of each constraint is non-negative. Okay? Of course, this requires that each constraint with a negative right-hand side should be multiplied by -1, right? Of course, if you multiply an inequality by any negative number, then the direction of the inequality should be reversed, right? And then we need to identify each constraint with an inequality. We need to identify each constraint with an equality or greater than or equal to sign. Okay? Because later in step number 3, we will add an artificial variable to each of these constraints, right? So in big M method, the first step, we need to identify the equality constraint or greater than equals constraint. Okay? Because we're going to add artificial variable for those constraints later on. Okay? Of course, less than equals constraint will not be considered. Okay? For this constraint, less than equal constraint, we can use slab variable as a basic variable, right? But for these two types of constraint, we're going to use artificial variable as the initial basic solution, basic variable, okay? And in step number 2, convert each inequality constraint to the standard form. This means if constraint is a less than constraint, we need to add a slab variable. If constraint is a greater than equal constraint, we subtract the surplus variable, right? And step number 3, if after step number 1 has been completed, the constraint is greater than equals or equality, then I said we need to add artificial variable, right? A sub I. And of course, we need to add sign restriction, which is each artificial variable should be greater than equals 0. Okay? And in step number 4, we need to introduce very big number, m. Okay? Very big positive number, actually. So if the given LP is a minimization problem, then we need to add m times a sub I, okay, for each artificial variable to the objective function, right? And if the original problem is maximization problem, we need to add negative m times a sub I to the objective function. And in the final step, step number 5, because each artificial variable will be in the starting basis. If the artificial variables are equal to 0 in the optimal solution, then we have found the optimal solution to the original problem. Okay? If any artificial variables have a positive value in the optimal solution, then the original problem is infeasible. Okay? And just to let you know that when an artificial variable leaves the basis, its color may be dropped, okay, anytime. Okay? Because the purpose of using the artificial variable is only to get the initial basic feasible solution. Okay? So once an artificial variable leaves the basis, then we no longer use that artificial variable in the future simplex table. Okay? Okay, then let's consider this example. So first, we need to modify the third constraint so that the right-hand side value is greater than equals 0, right? So we did it. And then next, add slab or surplus. Add slab variable or subtract surplus variable to convert inequalities to equation, right? And in that case, we can use negative g and s2 as basic variables in the objective row and the second constraint. And other constraints need artificial variable, right? So here, A1, A3, and A4 are the artificial variables added. Okay? So for the first and third and fourth row, negative m times a sub I is added to the objective. Of course, here m is very big number. Okay? Now we can construct an initial table based on this standard LP. and implement simplex algorithm to find the optimal solution. Because we want to maximize the objective function value if M is sufficiently large. And if there is a feasible solution for this given LP, then the artificial variables will be 0 in the optimal solution. Okay, then I'm going to give you an example for the big M method next time. And now let's move in the two-phase method, okay? Which is another way to eliminate artificial variable from the solution. Like I said, the two-phase method can be used as an alternative to the big M method, right? And actually, the first three steps are exactly the same as big M method, okay? That is, we need to add artificial variables to the same type of constraints as we did in the big M method, okay? And if you look at the step number 4, for now, we need to ignore the original LP's objective function. And instead, we need to solve an LP whose objective function is minimize W, which is the sum of all the artificial variables. And this is called the phase 1 LP. And the act of solving the phase 1 LP will force the artificial variable to be 0. Okay? So if the optimal value of W is greater than 0, then the original LP is infeasible. If the optimal value of W is equal to 0 and no artificial variables are in the optimal phase 1 basis, then we drop phase 1 objective function row and all the columns in the phase 1 table that corresponds to the artificial variable. And then start to solve phase 2 LP, which is the original problem with the optimal solution from phase 1 LP. Of course, the optimal solution to the phase 2 LP is the optimal solution to the original LP problem. Okay? Is that complicated? Okay, then let's consider this example number 1. Okay? So first, we need to modify the third constraint because it has negative value on the right-hand side, right? And we need to add slack and subtract surplus variable to convert inequalities to equation, right? So again, we can use negative g and s2 as the basic variable in the objective function row and the second constraint. And we do need artificial variables for all other constraints, right? So we can use negative g, a1, s2, and a3, and a4 as the basic variables initially, right? So actually, we need to find a basic solution which has a1 equals a3 equals a4 equals 0. So we introduce a new objective, which is phase 1 objective, and whose objective function is minimize the sum of all the artificial variables. And we can set equals W. Okay? And I said this is called the phase 1 LP. So basically, after phase 1 is completed, that is, after all the artificial variables are removed from the basis, we discard the phase 1 objective and artificial variables and use the current basic solution as the initial basic feasible solution for phase 2 LP, which optimizes the original objective. Okay? Okay, then now we add phase 1 row with negative W, okay, and artificial variables A1, A2, A3 to the initial table, like that. And we choose negative W, negative Z, A1, S2, A3, and A4 as the initial variable. Okay? And pivoting is required to eliminate the artificial variables from the first row. So how could you do that? If you do this, then all the artificial variable from the first row will be eliminated. Let's say the first row minus the third row minus fifth row minus sixth row becomes the first row in this table, right? Is that correct? So in this case, we have artificial variable in the objective function row, right? So this row, first row, minus the third row, then this one will be removed, right? Is that right? First row minus the third row, then 1 minus 1 becomes 0, right? Up here. Likewise, minus the fifth row, then this one will be removed because of this, right? Minus sixth row, then this one will be removed because of this one, right? So that way, we can eliminate artificial variable from the first row, right? However, we will have different values for here, and here, 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 and here, right? Because the first row minus third row minus fifth and sixth row becomes 0 minus 4 minus 1 minus 0 becomes negative 5, right? Likewise here, we have negative 3 because 0 minus 2 minus 1 minus 0 becomes negative 3, and so on. Okay? Does that make sense? And because we are minimizing W, we select x2 or x4 to enter the basis. And then let's arbitrarily select x2 to enter the basis. And note that the minimum ratio test is 0 in the last row. Okay? And next, we enter x4 into the basis. replacing H3 variable, right? Which is the basic variable on that row. Okay? And then finally, x1 variable enters the basis, replacing A1 artificial variable. Okay? And the resulting table says all the artificial variables are non-basic variable. Okay? Here, A1, A3, A4 are all non-basic variable, which means all of these artificial variables has the value of 0, right? So now we can drop the phase 1 objective row and the artificial variables from the table. Okay? And we now have an initial basic feasible solution for the original problem. So we begin phase 2, which optimizes the original objective. There is, besides, so in that case, we have reached the optimal solution, right? Because there is no positive relative profit in this table. So this is the optimal table. So in that case, x1, s2, x4, and x1 are the basic variables. But x3 and s1s are the non-basic variables. So x3 and s1 were how come I have different? Okay, no. Oh, so okay, so here x1, I was looking at different. x1 is 2, and x2 equals 4, x3 equals 2, and x4 equals 5. And because there is no positive relative profit on this table, this is the optimal table, right? And the corresponding optimal solution is negative g equals negative 32, which means g equals 32. Well, I think this is all for today. And next time, I'm going to give you some example problems to review what you've learned so far. Okay? So probably I will going to just give you one example problem, and then we're going to try to solve that LP by using both the big M method and two-phase method. Okay? Okay, then I will see you next time. Thank you very much.